So now what we're doing is we're now using a formal way of limits to deal with things that we've already dealt with before, such as holes in graphs, vertical asymptotes in graphs, horizontal asymptotes on graphs. We've also now introduced this idea of continuity, okay, if something is continuous. And there are different types of continuity, but basically continuity is, does it break apart like that? It could break apart like this, okay? But does it break apart? That's the basic idea of continuity. We don't want to make it any more complicated than that, although the notation can look very much more complicated. So we're going to summarize a few things here. So if we have left-hand limit and right-hand limit equal the same limit, then the limit is said to exist. Okay, so in this case here, so the green, what we're saying is from the left-hand side and the right-hand side is the same, we say that the limit exists. Okay, so this means that the limit, the two-sided limit as x approaches a of f of x, it equals our limit. If we have a situation where the left side and right side don't match, so as I approach from the right side and as I approach from the left side, if those two limits are different, okay, then we say that the limit does not exist. So this is a situation here where we say the left-hand side and right-hand side limits don't match, so it does not exist. And when it doesn't exist, we have what we call a jump discontinuity. Okay, here, this could be continuous or discontinuous. We need further criteria for continuity. This is what we're going to get into next. And continuity, we just want to simplify it, is continuity just means that we can draw the graph without lifting our pencil. And we want to formalize this by using limits. So a point is continuous if it follows the following criteria. So we look at two first. Left-hand limit and right-hand limit are equal. Okay, so we end up with from the left side and from the right side, it is equal. And not only that are they equal, but they're equal to where f of c is defined. So let's say that point is c. The limits have to be equal, and we have to fill in the dot. So that's what this means. Okay, and that's really just a formal definition using limits to determine continuity. It's just saying that we can draw straight through this. Okay, so again, we don't want to make it more complicated than it is. Continuity means we can draw straight through it. Okay, formally it looks like this. The left-hand limit and right-hand limit are equal to the value at point C. Now there are different types of continuity, and there are different types of discontinuity, and we're not going to get too much into it, but there's these different types. We have this removable discontinuity. There's a hole right there. This is also a removable discontinuity where we have a hole, but the point is defined somewhere. This one is called an infinite discontinuity in the middle, where it's going to the same place, but it's going to infinity, so it's discontinuous that way. And then we also have something called a jump discontinuity. And you're not going to be tested on the different types, but there are different types, and we can establish the limits differently to differentiate between the different types. Lastly, there's one more layer to these limits. Okay, this limit here, as x approaches 0 of cos of pi over x, what's happening is we end up dividing by 0. And as we divide by 0, right, as we divide by 0, we're approaching infinity, and we're approaching infinity very quickly. So what's happening is this value is becoming cosine of infinity. It's going through the angles faster and faster and faster as we approach 0. So what is the graph going to look like? Okay, so I'm just going to sketch what this graph looks like. Basically, as we are going towards 0 is going through the coast function quicker and quicker and quicker, and it's just going to go bounce back and forth between -1 and 1. So what ends up happening is, although it's bounded, okay, it's between +1 and -1, it never focuses in on any particular point. Because of that fact, we have to say that a limit does not exist. For a limit to exist, it has to focus in on one specific point. In this case, it doesn't, so we say that the limit does not exist.